Our first reporter is Mykhailo Zarichnyi, and his talk is named Hyperspaces of Convex Set Related to Idempotent Mathematics. Begin, please, Mykhailo Mikhailovich.
Very good, thank you. First of all, I wanted to thank the organizers for their kind invitation. I'm going to speak about the hyperspace of convex sets related to the so-called idempotent mathematics. And this is my joint talk with Natalia Mazurenko from the Carpathian University, and I'm from the National University of Lviv, named after Ivan Franko. And first of all, I would like to say a few words about the notion of hyperspace. Actually, if we read some books of science fiction writer Stanislaw Lem, for example, then one of his heroes asks another one who are in space, "What are you reading about?" And he replies, "I'm reading about the topology of hyperspaces." So this is also an informal notion, but I will continue informally, and I would like to tell that informally, a hyperspace is a space whose elements are sets of some space. And what is the main application of the notion of hyperspace? This is the following. We are able to regard any multi-valued map as a single valued map whose values are sets, but the sets are points of our hyperspace. So, and I briefly recall that if we have a metric space X with metric D, and if we have two compact subsets of X, and I suppose that these two subsets are non-empty, then the Hausdorff distance between these two sets, dh maybe, is the infimum of R's of positive numbers R, such that A, the first set A, is contained in the R neighborhood of B, and also B is contained in the R neighborhood of A. But in the absence of metric, we endow the hyperspace with the so-called Vitoris topology. This is the correct pronunciation, Vitoris. So given the topological space, we consider the following subsets of the hyperspace. First of all, U, in brackets, consists of the sets A, which are contained in U. And this set is, it consists of A, of the set, of the following sets. A intersection with U is not empty. So this is a hit and miss topology. Hit, an open set, and miss an open set. A closed set, I mean. Miss a closed set, this is to be contained in the complement, where U is open in X. In other topologies on the hyperspace are also considered. I will mention them later, but now I will remember a classical result, at least it is a known result, that if you consider the hyperspace of compact convex sets in the cube, a-dimensional cube, compact, convex, non-empty, well, such that the dimension of the cube is at least 2, and also we include omega, which means that this is countable power, so this is a Hilbert cube. Then the hyperspace is homomorphic to the Hilbert cube. This was proved by Nadler, Quinn, and Stavrokas, and this is a counterpart of the Curtis, Shorey, and West theorem that the hyperspace of all compact sets of any piano continuum is homomorphic to the Hilbert cube. Well, now I switch to the so-called idempotent mathematics, and I think, as I see, some talks will be related to this part of mathematics. So I say a few words, general words. So our standard traditional mathematics deals with R, with the set, with the field of real numbers R. But if we replace one of two of the operations, say multiplication or addition, if we replace it by an idempotent operation, we obtain the so-called idempotent mathematics. What kind of idempotent operation is important? Say maximum. So idempotence means that x operation x equals x. So maximum of x equals x. Similarly, minimum equals x. And this allows us to find the counterparts of almost all interesting notions of traditional mathematics in this idempotent mathematics. For example, this concerns the notion of convexity. So the following notion is the following: a set A in the Euclidean space Rn is maximum plus convex if this means this stands for maximum. V stands for epsilon, for maximum. If maximum coordinate-wise epsilon, coordinate-wise maximum of two vectors. The first vector is x. The second vector is y. Alpha is a constant which lies in negative infinity 0. I will explain later why. And this stands for addition. This is addition. Dot circled, encircled. Dot is addition. Now, why? Because negative infinity is the neutral element for maximum. Maximum of negative infinity and anything else is this anything else. Also, 0 is a neutral element for addition, which serves for multiplication. So this, in traditional mathematics, this corresponds to 0, 1. So we have two coefficients, but we do not need here one of the coefficients. This is a technical trick, but actually one could have two coefficients alpha and beta such that their maximum equals 0. But one can simply reduce this for this formula. So we obtain the notion of maximum plus convex set. And this picture definitely would help. So typical segments connecting 2 points in plane with respect to this notion of convexity as the following. So x1, if we try to connect x1 and x2 minimal by a minimal segment, we obtain something like that. This is the diagonal. If the position, mutual position, is like x2 and x3, so we have such a broken line. And for x1, x3, we have this one. So set in plane is maximum plus convex if it contains, together with its 2 points, it contains the segment which connects them. Well, and now the hyperspace of the compact maximum plus convex sets in the tau power of R is denoted by MPCC, maximum plus compact convex, R of R tau to the power of tau. Here tau is a cardinal number, and the following facts are known. First of all, that if the space is at least 2-dimensional, at most is finite dimensional, then this hyperspace is homomorphic to the punctured Hilbert cube, the complement of a point to the Hilbert cube, to the point in the Hilbert cube, and in the case of infinite cardinal tau, we have that it is homomorphic to R tau in 2 cases. First one, when this is the countable power, And the next, when we have the power omega-1, the first uncountable cardinal. And it turns out that after that, nothing is known, so we cannot prove something like that because the space is not an absolute retract for larger values of the cardinal. Well, why such a picture? Because well, we should apply the technique of inverse spectra, which was developed by Evgeny Shchepin. And it shows that if we consider the weight omega-1, then we can decompose this into the inverse system consisting of metrizable things, which is ordered, well-ordered system, and we simply approximate this limit space by smaller metrizable spaces with nice projections. These projections could be described as trivial bundles, and therefore we obtain r to the power omega-1 in this situation. And why not absolute retract? Also, we have to apply this analysis of inverse spectra, inverse systems, as we say. Also, in compact case, we can also have such the following results, that this maximum plus convex of I to the power tau is homeomorphic to Q to the Hilbert cube, right? And in the case of I to the power omega-1, we obtain the hyperspace homeomorphic to I to the power omega-1. And also for the higher weights, we cannot, we do not have an absolute retract. Well, now let us consider another type of convexity. In this case, we have two idempotent operations. The first one is maximum, which stands for addition. This one, this is the maximum, and the second one is the minimum, which stands for like multiplication. And now, what is the neutral element for the maximum? This is negative infinity. Maximum of negative infinity, and anything else is anything else. Minimum of anything of infinity and anything else, plus infinity. This stands for plus infinity, plus infinity. Therefore, we have a counterpart of the notion of convexity. So we have that the alpha times x plus beta times y. This is convex combination for what alpha? Alpha plus beta should be 1. But 1 is infinity, is neutral element for minimum, and plus is maximum. So we have for two numbers, one of them should be infinity. I could not trace back who is the author of this notion, so my citation is not the very original, let me say so. And what are the typical segments in the two-dimensional case? They are drawn here. So if you have 2 points, and here this stands for the diagonal for the diagonal y equals 2x. Given 2 points here, we connect them by this segment. If well, they are located like that, we have such a broken line. Well, so all the possible cases are here. And also, this is a known result. So the hyperspace of compact maximum convex sets. This is noted by MMCC of R tau. Also here, tau is a cardinal number. And for the hyperspaces, as I told this, one can prove similar facts for the hyperspaces which I mentioned above. Well, so we see that to the power omega-1, they are homeomorphic. And the question is, are the hyperspaces always homeomorphic? So for all cardinals. We do not know anything about these hyperspaces, even if they are absolute tracts. So this is for R to the power tau, and similar question can be formulated for this is I tau. Well, and also obviously these results can be formulated and obtained in other linear spaces, like function spaces like C of X for compact X. So we can introduce the notion of maximum plus convexity in this case, and also for maximum in convexity here. So, for example, in the separable case, the corresponding hyperspaces are homomorphic to the Hilbert space, separable Hilbert space. Well, now about the Feld topology. Feld topology, the difference between the Feld topology and the Witter's topology is the following. We consider the sets of the form A, which is a subset of W, where W has compact complement. So we miss compact sets, not all the closed set, but we miss compact sets. And Sakai and Young, they proved that they considered the hyperspace of ordinary convex sets of the Euclidean space, and they proved, well, this is a trivial case, so we exclude it. So this is the hyperspace is homomorphic to R to the power of n multiplied by Q. Well, and we can prove the similar results, and this is what I wanted to say here, basically. And this is not everything, but first of all, that these hyperspaces endowed with the Feld topology, they are homeomorphic to R n multiplied by Q. Well, and one more thing I wanted to tell, that there are plenty of possibilities in the idempotent mathematics to produce new notions of convexity. So for example, I want to mention only one of them. And for different reasons, it would be convenient not to work in R to the power of tau, but to 0,1 to the power 0,1 to the power of tau. And to this end, we introduce the notion of the following operation. A star B is maximum of A plus B minus 1, 0. So we add A and B, numbers between 0 and 1, and subtract 1. If we are below 0, we replace this by 0. And we introduce the notion of the Łukasiewicz. This is called the Łukasiewicz T-norm. Łukasiewicz, this is my genuine Polish pronunciation, Łukasiewicz. And a subset is called Łukasiewicz convex if for any xy in A and any t, we have the following combination belongs to A. And the hyperspace of the Łukasiewicz compact convex sets is denoted by L. This is L, I forgot what is, I forgot the word. Перекреслили. Anyway,
Crossed out.
so this is not,
Crossed out, maybe.
Crossed out. No,
Kreskowane, prawda?
Kreskowane. Dziękuję bardzo, panie profesorze. Tak, kreskowane. And for these hyperspaces, one can prove the counterparts of the results mentioned above, and how to consider these results in non-compact case. We do not use R here, but simply open segment 0,1 to the power of tau, and my time is over. I want to thank you very much for your patience.